Good morning, physics students. Today we're going to talk about impulse. So in the last video, we started to discuss momentum, and we said momentum is vector. It is the mass times the velocity, and if you're doing the change in momentum, it's the mass times the final velocity minus the mass times the initial velocity. And we also said that, what else do we say about momentum? We did some sample problems. So what we're going to do today is we're going to talk about this concept called impulse. And I always, when we're in class, we do an egg throw demonstration. So the first egg we throw, we put a garbage bag up against the wall, and of course the egg absolutely shatters. Then we hold up a bed sheet, and I tell students, try as hard as you can to break the egg, throwing it into a bed sheet. And as far as I know, it is impossible. It can't be done. And then we talk about the reason why, and I'll show them a slow motion video. And what they see is that when the egg hits the sheet, there's this long process of deforming the sheet. The egg moves the sheet in, and the egg and the sheet move together. So what we're seeing there is some collision physics. And the collision for the egg into the sheet lasts longer than it does for the egg against the wall. And in a sense, that's what impulse is. Impulse. We're going to compare the time over which a force is exerted, and this is in a collision. We have to have a collision. In a collision. Whoops, C-O, it's an O, L-L-I-S-I-O-N. And basically, that's the definition for impulse. So impulse, which is a letter, our symbol is a capital letter J, is equal to force times time. Well, what was our unit for force? That was a Newton. What was our unit for time? That is a second. So you can use the unit here as a Newton second, or remember that a Newton is a kilogram meter squared per second squared. So if I use the long form for Newton, which is kilogram meter squared over second squared, and I multiply that by seconds, this seconds is going to cancel, and I'm going to end up with kilogram meter per second. So our unit for impulse is kilogram meter per second or Newton second. You'll see it both ways. And if you notice, this is the same unit that we had for momentum. Is that significant? Yeah, it really kind of is. So we said that momentum, or let's do change in momentum, delta P, is mass times the final velocity minus mass times the initial velocity. Well, the fact that they have the same unit tells you that the change in momentum and impulse are related. And it turns out they are equal. So the change in momentum, that should be a J. Let me get out my whiteout 1 second, because that should really be a J, not an I. And I don't want to start the recording over. So if you'll bear with me here, we'll do that. Okay, so it's going to be equal to, now in some problems and in some textbooks, you'll see impulse as I or a capital I. As far as I know, on AP Physics, they use a capital J. But this is going to be equal to force times time. And if this looks a little bit familiar, it should. This is very much similar to the work energy theorem, where we had, I call it, this is my term, a swing equation, where on one side you have one entity, on the other side you have a different entity. So we had that kinetic energy, the change in kinetic energy was equal to energy for work energy theorem. So here we have that the change in momentum is equal to the impulse. The other way we can look at this, if we do an FT graph, so let's do axis here. And this is going to be force times time. The other thing that we can know about impulse, so if I have a line here, if I find the area under that curve, and if you're in calculus, you'll recognize this is an integral, this area is also equal to impulse. So when we go through our practice problems, we're going to see that we are going to use the graphing as well. And by the way, this is a part 1. This is going to be at least 2 parts, possibly 3. All right, so let's look at our first sample problem. A car at rest is pushed by 3 people with a combined force of 305 newtons. What is the momentum of the car after 12 seconds? If the mass of the car is 1,360 kilograms, what is its velocity at 12 seconds? Now, you have to kind of assume that at this point, the people are pushing in the same direction. So we know that the net force is 305 newtons. We don't really need to do a diagram on this one, although often it is beneficial to do a diagram. So let's start off with part A. So I like to write out my equation each time. We have delta P equals J, and that is equal to force, times time. Well, my force is 305 newtons and my time is 12 seconds. So this one's pretty simple. I'm going to have 305 times 12, which is going to give me 3,660 kilogram meters per second. Well, you're saying to yourself, wait a minute, we just solved for impulse. We didn't solve for momentum. Remember, they're the same. So I can use this part of the equation to solve for momentum as well. And if I want to solve for impulse, I can use the delta P value that we had up here. Whoops, my pen does not want to work today. For impulse, because they go hand in hand. So then finally, it says, if the mass of the car is 1,360 kilograms, what is its velocity at 12 seconds? Well, let me bring the rest of my formula down here. I have mvf minus mvo. So can I use this expanded equation to solve for my the velocity at 12 seconds? Sure. I know that my initial velocity is 0. And I know that my mass is 1,360. I know that my change in momentum is 3,660. So I can use this 1,360 kilograms times my final velocity minus 1,360. My initial velocity was 0. This is going to be equal to 3,660. When I solve for my final velocity, I find out that it is 2.69 seconds. Now, you might be saying to yourself, hold on, when I looked at this, I know that force is mass times acceleration, so I can use Newton's second here and find the acceleration. I have the time and I have the initial velocity. I could have used kinematics. Yes, you absolutely could. And at this point in physics, what you're seeing is there are multiple ways to solve these problems. But for this one, if you had used Newton's second and kinematics, you would have been using 2 equations at least. Here, you can do it all with 1 equation, which is kind of nice. It's a little bit faster. All right, let's look at one more sample problem in this part, and then I'll move on to a part 2. So let me scroll down here, move my camera. All right, so we have a top tennis player. A tennis ball may leave the racket on the serve with a speed of 55 meters per second. Let's see if I can get this centered, which is about 120 miles per hour if you're interested. And if the ball has a mass of 0.06 kilograms and is in contact with the racket for about 4 milliseconds. Is that milliseconds? It is. Estimate the average force on the ball. Would this force be large enough to lift a 60 kilogram person? Well, this part of the problem is going to be comparative. We really don't need that. We'll use that later. What we want to do right now is we want to find the force that's required to the average force on the ball. So let's go to our expanded equation again. Go to purple here. So we know that we have mvf minus mvo is equal to delta P is equal to impulse is equal to force times time. Well, I have time, which is nice. I have my final velocity is going to be 0, and my initial velocity it gives me. So I can use this to solve for time. So let's go with this value is going to be 0.06. 0.06. This is going to be 0. This is 55. And I don't have to put this in the middle. I can just write this out this way. So I have force. Now this is milliseconds. So remember, we have to go milli, centi, deci, and so this is going to be 0.004. And when I solve for force, I get that this is negative 825 newtons. So what's up with this negative? You have to understand too that impulse is a vector. So if I have a tennis racket, back to black. Here's my tennis racket. And I have the ball coming in. The ball is exerting a force on the tennis racket. That means the tennis racket is exerting a force back on the ball. So we're looking at the average force on the ball, and we're assuming that the ball is coming in with a positive force, and that means the counter force is going to be negative. That would also make the impulse negative. So you could have done this with kinematics because we had V sub O, V sub F, X, A, T, and we had mass was 0.06. We had time was 0.004. We had, this is 0, this is 55. So we could have used kinematics to solve for acceleration and then use Newton's second. But again, we did it with one equation. So the second part says, would this force be large enough to lift a 60-kilogram person? Well, what do we need to lift a 60-kilogram person? Remember, 60 kilograms is mass. To find force, we're talking about weight. So for part B, we would take the 60 kilograms times 9.81, and that's going to give us 588.6 newtons. So yeah, if we could apply this force to a person, it would lift them off the ground, even though it would be for, a short time. Okay, that takes us through our intro and 2 sample problems. I think in part 2, we will keep our practice problems going. All right, go on to part 2 then.